Hi, this is Mrs. LaBarbara. This is Physics Chapter 9, Current Electricity, Video 2. Today's topic is electrical resistance. The objectives are note definition, equation for electrical resistance, understand factors affect resistance, be able to calculate electrical resistance, resistivity, length, or cross-sectional area of an object, to be able to select graphs showing the relationship between the resistance and the length, cross-sectional area, resistivity, and the temperature. Be able to use resistivity to determine the composition of an object. Be able to explain the difference between resistance and resistivity. Be able to determine the effect of changing the length, cross-sectional area, or temperature on the resistance of an object. Definition: resistance is defined as opposition to current. Its unit is ohm. So this is named after scientist George Ohm. The factors that affect resistance are resistivity, length, and cross-sectional area. Resistivity depends on two things, the material and the temperature. So for example, a copper wire at 20 Celsius degrees have a certain resistivity. If you increase that temperature, resistivity would increase. That means the resistance would increase. This is because when the temperature increases, you learn in chemistry the object start to vibrate faster. So when the object start to vibrate faster, it will have more chance for the electron to collide with the atom inside the wire. Okay, so how is the resistance related to resistivity, length, and cross-sectional area? So R is, as you can see, is directly related to resistivity. The more resistivity you have, the more resistance you have. And R is directly related to the length. So the longer the wire, the more resistance the wire will have. And R is inversely related to area. The wider the wire, the less resistance you have. Think about resistance or how electrons travel through the wire is very similar to car traveling through a highway. So the longer the highway, the more chance the car will stuck in traffic. However, the wider the highway, the easier for the car to travel through. So this is kind of like similar in that sense. To build an ideal conductor with the smallest possible resistance, you would select one that is short, fat, cold material that has low resistivity. Short means the L is small, fat means A is big, cold, and the material has low resistivity gives us a very small rho. By the way, this is pronounced as rho, R-H-O. Resistance graphs, we already said, R is directly proportional to rho, resistivity. R is directly proportional to the length, since as the temperature increases, resistivity increases. So R is directly proportional to the temperature. R is inversely proportional to the area. The wider the wire, the lower the resistance. So the difference between resistance and resistivity are this. Resistivity only depends on the two things, the material and the temperature. But R, the resistance, also depends on the length of the wire and the area of the wire. Let's take a look at this example. Determine the resistance of 1 meter long copper wire at 20 degrees Celsius with a cross-sectional area of 0.01 meter squared. So use the equation we have, R equals rho L over A. Rho, where do we find this? From the reference table. This 20 degrees tell us the information is in the reference table. We don't really use 20 degrees in our calculations. So we should be able to find this number, 1.72 times 10 to the negative 8 ohm times a meter. This is resistivity times the length of the wire is 1 meter. The area of the wire is 0.01 meter squared. So this is a meter squared, not the whole thing squared. Okay, so you should have 1.72 times 10 to the negative 6 ohms. Another example, a piece of wire that has a length of 5 times 10 to the 7 meters. This is much, much longer. And a cross-sectional area 0.025 meters squared has a resistance of 31.8 ohms. What is the composition of this wire? What they are asking is what is the resistivity? Then once you have the resistivity, you can look in your reference table to match the material. So R equals rho L over A. You're trying to find a rho. Rho equals to R times A divided by L. Plug everything in. You have 1.59 times 10 to the negative 8 ohms times meter. So check your reference table. The material is silver according to the reference table. So here is one thing. A lot of times you'll ask you the resistivity. So sometimes we'll calculate the resistivity, but maybe that material may not be listed in the reference table. It does not mean you're wrong, because reference table has very limited number of materials. Another example, a incandescent light bulb is supplied with constant potential difference of 120 volts. As the filament of the bulb heats up, what happens to resistance? As you can see, if it heats up, the temperature increases. Therefore, resistivity increases. Therefore, resistance has to increase. Now, what happens to current? Remember, resistance is to resist a current. So if resistance increases, current has to decrease. Another example, a 12-meter length of copper wire has a resistance of 1.5 ohms. How long must be an aluminum wire with the same cross-sectional area B to have the same resistance? So we have the same resistance, we have the same cross-sectional area, so what is the length of the aluminum wire has to be? So here is the equation we know. We know R and A has to be the same. Copper wire is wire 1, aluminum wire is wire 2. R1 equals to R2, they have the same resistance. And they also have the same area. That means the resistivity of a copper wire times the length of the copper wire has to be equals to resistance of the aluminum wire times the length of aluminum wire, right? So from the reference table, we can find the resistivity for copper wire and aluminum wire. And we know the length already for the copper wire, so we have to find the length of L2. L2 equals rho 1 L1 divided by rho 2. These are in your reference table. Your answer should be 7.32 meters. It's much shorter. That is because the aluminum wire has a bigger resistivity. Let's take a look at this example. A copper wire at 20 degrees Celsius has a length of 10 meters and a cross-sectional area of 1 times 10 to negative 3 meters squared. If the wire is stretched to become longer and thinner, and still at a 20 degree remains to 20 degree Celsius. So what effect does this stretching have on wire's resistivity? Remember, I talked about resistivity only depends on two things, the material and the temperature. Looks like the wire did not change. It's still copper. The temperature didn't change. It's still 20 degrees Celsius, so resistivity has to remain the same. Okay, that's it for today. Thanks for watching. See you next time.